Well, welcome everybody. We'll just wait a minute while people enter into the webinar. Okay, so I think we'll try and start on time today. So good morning and good afternoon, everyone, and welcome to the latest in the Earth Observation webinar series. My name is Caroline Paulson. I'm a committee member of EOA, and I'm also a satellite scientist at the Bureau of Meteorology. So this topic, using space-based Earth observations to understand and tackle the climate challenge, is one that I care about, and I'm really happy to have some excellent speakers today to talk about it. But before we get started, I would like to acknowledge and pay respects to the Wurundjeri people of the Kulin Nation, the lands on which I stand. And I would also like to acknowledge the traditional custodians of the lands that we are gathered on across all states and territories, and to pay my respects to the elders past, present and emerging. As we pursue a scientific understanding to live within our natural environment, we also pay respect to the knowledge deeply ingrained in the Aboriginal and Torres Strait Islander history and culture. I think that's very appropriate for today. So just a little bit of housekeeping. I just want to remind people that this seminar is recorded and also the chat is saved as well. And also to abide by the EOA Code of Conduct, which is to treat people with respect. And I'd like to thank Larissa Marfan from University of Queensland and EOA for helping with the organisation of this meeting. Okay, so the idea behind setting up this webinar was the EOA currently has a number of working groups, one on calibration and validation, another the small business, and we wanted to see if there was enough interest to have another working group for Earth observation in climate. So we want to see if there's any interest in the community and also what that remit might be. So is it raising awareness like we are doing today with a number of topics? Is it networking between policymakers and scientists, or identifying gaps in the data or in the quality of the data? We're very open to ideas, and there'll be a chance for you to express your interest and express your opinion on what the remit should be at the end of the seminar, or to contact EOA after the webinar. Okay, so I've really just got one slide as an introduction, and it's a quote. So if you can't measure it, you can't manage it. And that's a really nice quote from the President of the United Nations General Assembly at the Climate COP, which was held in Poland. And she was summing up how crucial satellites were for measuring climate change. So without the observations, there would be very little evidence for which to inform our decision makers for environmental policies, including those aimed at mitigation and adaptation to climate change. And it's also important to see that those mitigation and adaptation efforts have been successful. So we have 4 presenters today. The first is our very own EOA member, Dr. Anthony Rea, who is also the Director of Infrastructure Department at GCOS, Secretariat at WMO in Geneva. And then we have 3 speakers who I'll introduce prior to their talks, covering that whole Earth system, because the climate is all of land, sea and atmosphere. Okay, and then there'll be a question and answer session at the end. Okay, so I think we can get started with our introduction. So I welcome Anthony to share his screen. I'll stop sharing mine. And Anthony is the Director of Infrastructure Department at the Global Climate Observing System, Secretariat at WMO in Geneva, but I think he's joining us from Melbourne today.
I am, Carolyn. Thanks very much for the introduction, and good afternoon and perhaps good morning, everyone. Just give me 1 second and I will pull my screen up. Share. Okay, so hopefully you are seeing that in presentation mode. So I'm going to give just a quick overview on the Global Climate Observing System, and it will dovetail nicely into the 3 presentations we have this afternoon, because GCOS is organised around three panels: the atmosphere panel, the ocean panel, and the terrestrial panel. So covering the 3 domains of the atmosphere, the ocean, and the land. GCOS works towards a world where users have free access. So one of the focus areas of GCOS is not just coordinating global observing systems, but it is also providing free and open access to data. It's a kind of a pathway between user requirements on the one end and the coordination of global climate observations on the other. And it does that coordination through a number of mechanisms. There's a working group on climate that's jointly organised between the Committee on Earth Observation Satellites, CEOS, and the Coordination Group on Meteorological Satellites, CGMS. And the working group on climate essentially takes the outputs from GCOS, the implementation plan and the status report, and tries to translate that into action on behalf of the satellite operators to observe these essential climate variables that GCOS has developed. So GCOS, I think many people working in the climate space are aware of the idea or the concept of essential climate variables. These were developed within the GCOS framework and are maintained through, as I mentioned, the GCOS status report and implementation plan. Importantly, GCOS doesn't take any observations. It aggregates observations and coordinates the global observations from networks operated by many different agencies and many global systems. There's a kind of a cycle that GCOS goes through, which starts with the status report. So how are we doing in terms of measuring these essential climate variables? We delivered a status report to COP26 in Glasgow in 2021, and then at COP 2027 last year in Sharm el-Sheikh, the GCOS implementation plan was delivered, which has a whole bunch of actions, and the actions are framed around the types of people who were responding to them. So there are actions for Met agencies, but there are also actions for satellite operators within the implementation plan. We're going through another cycle. We're at the start of the cycle now. There'll be a status report probably in 2025, which will look at how we're doing against the current implementation plan, and there will be a new implementation plan, I expect, in 2026. So the idea of essential climate variables is a physical, chemical, or biochemical variables that characterize the Earth's climate. They're not standalone variables. They're part of a broader concept, and they're founded on climate science and observational capability and infrastructure, but they provide the empirical evidence to understand and predict the evolution of the climate, to guide mitigation and adaptation, assess risk, and to underpin climate services. I'm going to go through pretty quickly. There are, as I mentioned, we have ECVs aiming to monitor the climate system as a whole, covering the interlinked Earth's energy balance and the carbon and water cycles. And the biosphere is also important, particularly when we're talking about the carbon cycle. And you can see here one characterization of the ECVs around the different cycles: hydrological cycle, carbon cycle, the biosphere, and the energy balance. Just finally, GCOS coordinates a wide range of networks, including the Global Ocean Observing System, incorporates observations from the Global Observing System, from WMO's the Integrated Global Observing System. I already mentioned CEOS CGMS working group, and there are a range of others. It's supported by external donations. The Secretariat's supported by external donations, and we have very important partners in Copernicus and the European Commission, and also the US State Department. In in the interest of time, I'll stop there and hand back to you, Carolyn. I hope that gives at least a little overview, and I think we can make the slides available. Thanks very much.
Thanks very much, Anthony. And I think that's a good entry point into the next talk, which will be Rob. So Rob Mattam is a principal sea ice research scientist at the Australian Antarctic Division and a member of the Australian Centre for Excellence in Antarctic Science. His passion for polar research began many annual sea ice cycles ago when he joined the Scott Polar Research Institute in Cambridge, UK. And he was then very fortunate to spend 3 years as a postdoc in the Oceans and Ice branch of NASA Goddard Space Flight Center in the US before moving to Tasmania in 1992. In spite of suffering terrible seasickness, he has participated in 15 sea ice field measurement campaigns in both Antarctica and the Arctic, and his current research interests include the nature drivers and effects of sea ice change and variability, the role of snow in the sea ice system, and linkages between Antarctic sea ice and ice shelf stability, all with strong reliance on remote sensing. He loves cross-disciplinary research, and his work has benefited greatly from collaborations with many wonderful colleagues. I hope you find some here. Thank you.
Thank you very much indeed, Caroline. And hello, everyone, and thank you for inviting me. I'm put down as talking about the ocean. Well, actually, I'm going to talk about the frozen ocean. It's Antarctica's sea ice cover, and particularly change and variability and the role of using satellites in investigating that. Oh, I'm sorry, the screen's stuck at the moment. Oh, there we go. So first up, a quick primer on what sea ice is. Well, it's effectively frozen seawater at -1.8, not to be confused with the ice sheet and the icebergs, of course. And it's actually made up of two elements. One is pack ice, that's made up of the elements which are flows. They're mobile and dynamic. They move with winds and currents. They evolve over time. They form a thin discontinuous veneer over the ocean surface, and they're mainly less than 1 year old. And importantly, they intercept and accumulate a snow cover, which substantially impacts the properties and the optical characteristics of the ice itself. And secondly, we've got something called fast ice, which is far from fast. It's actually stationary and consolidated. It's a narrow band of sea ice, which is actually locked onto the ice sheet margins, and it's pinned in place by also grounded icebergs. So what happens to sea ice is really, really important for a wide range of issues. For one thing, sea ice around Antarctica, it forms a vast area, and it's seasonably highly variable from about 3 million square kilometers in summer out to about 19 million square kilometers in wintertime. And you can see a map of Australia there to give you some idea of the scale of this. And the ice sheet is 14 million square kilometers there. Now, importantly, the ice forms a very bright surface, and compared to the ocean, which is dark, it reflects a lot of incoming solar radiation back out to space. This helps to moderate the global temperature. Not only this, but by forming a veneer over the ocean surface, it substantially modulates ocean atmosphere exchanges of heat, gases, and momentum. That's wind energy between the atmosphere and the ocean. It exerts a controlling influence on weather and climate, weather patterns around the Southern Ocean, and including our weather in Australia. It influences the characteristics of the Southern Ocean itself, the circulation of the global ocean through its melt and freezing. It has a strong influence too on the biology of the Southern Ocean. Primary production, krill, penguins, whales, etc., are all heavily reliant on sea ice. And also, and I'm not going to cover it in this talk, but it plays a role in stabilizing the ice sheet and ice sheet margins. And also it's a key factor in human activities around Antarctica. So sea ice change has serious wide-ranging consequences. It's sensitive. It's not only sensitive to climate change, but it also plays an active role in modulating that climate change. And in the Arctic, we've seen that sea ice loss has actually amplified warming at high latitudes. So it's a major challenge to measure and monitor. However, it's, as I said, it's vast, remote, it's extremely inhospitable, it's highly dynamic, and there's a complex interplay of processes going on involving dynamics and thermodynamics. So it's over a wide range of key spatial and temporal scales, from minuscule up to 1,000 kilometers, and of course, daily or hourly minutes through to years and decadal, etc., etc. And unfortunately, it's shrouded in polar darkness and cloud for much of the time. So there's a crucial role of satellites in monitoring and measuring what's happening to sea ice. And not one satellite sensor, it's like in every field, is perfect for measuring sea ice. So what we try to do is use a complementary range of different satellites, from visible, thermal infrared through microwave. And the satellites not only are important for sensing, but also for data relay, positioning, navigation of systems that we put onto the sea ice, like buoys. And this is the way we carry out our research, is to use the satellite with in situ measurements and autonomous platforms, and also coupled models. So the big picture is quite scary at the moment, and it's a news item at the moment. We're very heavily reliant on the satellite passive microwave record. It gives a daily measure of ice concentration and coverage around Antarctica, stretching back to 1979. And this is showing that things were going along quite nicely. There was an increase in overall sea ice coverage around Antarctica until about 2014. Then there was an abrupt dip. And the image on the right-hand side shows the current situation. The line around the current sea ice coverage is the mean coverage over the entire satellite record. So you can see there's a lot less sea ice. And if you look at the annual record on the left, and also today's record on the right-hand side, you can see that there's been a strong departure from the mean situation. And in fact, in early July, Antarctic sea ice coverage was about 6.4 standard deviations below the mean. So something quite dramatic is going on, and we're entering uncharted territory, and it leads us to believe that maybe there's a regime shift that's going on. So there's not only a shift in the extent of sea ice, but importantly, there's a shift in the seasonality of sea ice and the change in seasonality. On the left is a map showing annual duration of sea ice, again from that satellite passive microwave record for this last year. And you can see lots of reds and not many blues. So the sea ice season is a lot shorter in many places around Antarctica. And on the right-hand side is the duration trend map over a long period. And this shows that there's been a shift away from a regionality to a circumpolar pattern in ice loss. So there are many pressing issues here, determining the nature and impacts. What are the processes? And a major concern is feedbacks. And one is the ice albedo feedback. Less sea ice, more open ocean, more sunlight heating that open ocean, leading to less sea ice, etc., etc. So moving on to the satellite sensors themselves and the satellite missions, we're very a synthetic aperture radar is a very powerful sensor in sea ice research and monitoring. It gives information on ice type development, but also importantly, the velocity and dynamic fields of sea ice and whether these are changing. Now, in order to do this, you need repeat measurements over the same area to carry out image cross correlation. And a map on the left shows one such derivation of ice motion, and motion of the ice and deformation are extremely important. They influence not only the coverage and the concentration, but also the formation of melt, the thickness distribution, the transport of fresh water and its budget, and also safe shipping around Antarctica. And this is all key input to improving models. So a major issue for us is that SAR coverage around the Antarctic is relatively poor. What we really would like is more extensive routine repeat coverage for monitoring and change detection rather, and the flexibility to target areas where certain events are occurring or where we have field experiments and process studies. And the image on the right shows that in the Central Arctic, the situation is quite different. There's tended to be quite substantial coverage, and this has enabled people to provide these maps of the dynamic characteristics of the sea ice on a regular basis. Moving on very quickly to moderate resolution visible to thermal infrared, such as MODIS. It's cloud cover, but it provides broad coverage, and it's crucial for fast ice monitoring around the coast. Alex Fraser and others have put together this beautiful long-term data set of fast ice. It's based upon compositing of the image to get rid of cloud cover, and it provides the first ever trend analysis or long time series of fast ice coverage around Antarctica. Such imagery is also important for detecting rather abrupt changes in the coastal areas around Antarctica. This shows what happened when the Mertz Glacier tongue calved in 2010, and it had quite a dramatic impact on the ice conditions and icescape around the coastal Antarctica near Dumont d'Urville Base. And this has implications for global circulation. And also, this is quite a scary image. It's an image, a current one provided by Phil Reed of the Bureau of Meteorology, and it shows the importance of getting moderate visible and thermal infrared for assessing sea ice ocean interactions. And you can see here that there's a strong correlation between sea surface temperature anomalies, which are very strong at the moment in the Southern Ocean, and loss of sea ice around Antarctica. And moving very quickly, what we'd really like to use but haven't used very much at all due to lack of availability is high resolution visible and thermal infrared imagery, the kind of images that are used in terrestrial situations a lot, Landsat and SPOT, etc. These are again cloud effective, but they provide a tremendous amount of detail on the sea ice coverage. And here you see information on the classification of the sea ice, the size of the flows and the morphology. And importantly, this kind of information is key to interpreting lower resolution and microwave imagery. And what we would also really love, but haven't used very much because it's been very expensive, is ultra high resolution, kind of meter scale resolution imagery. And you can see the image on the left there is a Maxar satellite image, and it shows a tremendous amount of detail on the flow size distribution. And this would be extremely helpful in our process studies around Antarctica.
1 minute, Rob.
Thank you very much. A critical gap for us is snow cover and sea ice thickness. Now, satellite altimeters really hold the key to this. Through if we measure the surface and measure the surface of the ocean, then you can derive information through Archimedes' principle on the thickness of the sea ice and the snow cover. But there's a large current uncertainty in this, and we need independent data for calibration and validation. This is where Australia could come in. We could play a key role in validating, taking surface measurements, near surface measurements, and validating Antarctic sea ice measurements. So the future outlook, and this is a home straight, is a critical need for continuation of key time series, improved SAR coverage, access to high vis, etc. Passive microwave sea ice concentration is vulnerable. There are a few satellite sensors coming up, which are key. And I won't read out all of these just due to time considerations, but I'm happy to provide this slide, or you can look at it at your leisure when you look at this talk again, it being recorded. And there's a few links there to the particular satellite sensors, which will hopefully be important in the future. And here's a bit of further information on sea ice. If anyone's interested, there are a few online publications here which may be of relevance. And just to say thank you and acknowledge many colleagues and Sorry for the rush there. I'd just like to put out a big acknowledgement to Phil Reed, who's a wonderful colleague and who plays a key role in producing a lot of this satellite imagery. So thank you very much indeed.
Thank you very much. Okay, so much data there. It's quite inspiring. So our next speaker, we're going to the atmosphere, and it's Professor Peter Rayner. Peter Rayner has been studying the sources and sinks of greenhouse gases since the early 1990s. He's focused on inversion techniques in which measurements of gaseous concentration are combined with atmospheric models to back calculate the distribution of sources and sinks in space and time. In the early 2000s, he calculated the precision requirements for satellite measurements of carbon dioxide to improve our knowledge of CO2 fluxes. And this work helped stimulate several current and future satellite missions measuring carbon dioxide and methane. He's since extended the statistical calculations of fluxes to include detailed process models that allow other types of Earth observation data to be included. And he's worked in Australia, the US and France. And he's a previous winner of the Priestley Research Medal from AMOS. So thank you very much, Peter, for talking to us. And I think Larissa is going to be putting up your slides in a minute, and I'll tell you when they're up.
Right. Firstly, can everybody hear me? Am I safely off mute?
Yes, you're off mute and your slides are up.
Excellent. All right, let's start with the title slide. So I'm getting Larissa to manage my slides because I'm totally blind. So it's managing the visuals is one of these things I'm really bad at. All right, so let's move to the outline. Here's a quick outline of what I'm going to talk about. I'm going to talk about remote sensing of greenhouse gases, as you might have expected from that bio, and really just why do we do it? How do we do it? What's the current state of play? I'm going to give a couple of examples, a couple of Australian examples. What's the current state of play and what's happening in the near future? And what do we think Australia's role might be? All right, next slide. So why do we measure greenhouse gases? You might think it's so that we can understand their impact on the climate. And in fact, that's not the main reason. We actually need very few measurements to do that because the climate forcing we get from greenhouse gases is pretty well mixed throughout the atmosphere. And so we could do that with very few measurements indeed. The main reason that we do these measurements is to try and estimate the sources and sinks of greenhouse gases so that we can manage them. And that seems a rather indirect way of doing things. And we need to do that simply because directly measuring them is too hard. For most of the greenhouse gases, most points on the Earth are potential sources and sinks. And so there's no way that we can deploy direct measurement technology to do that. And so we tend to measure them indirectly instead. Next slide. So here's a rough schematic of how that might work. So let's think first about measuring at a point, measuring an in situ measurement, we might say, and we've got a couple of red squares where we might have measurements, and we've got circles that are potential sources. And because the wind keeps changing direction, we can use the time variation of concentrations across these two observing sites, coupled with knowledge of what the wind is doing, to essentially back calculate the relative contribution of those two sources and sinks to the concentrations that we actually measure. So it's really important to remember that we're measuring concentrations, but we're estimating emissions. They're two quite different things. Now, that's not quite as straightforward as it looks, simply because the atmosphere doesn't behave as nicely as that. It tends to spread emissions into plumes, and that rate of spread can look very different under different atmospheric conditions. So we tend to use atmospheric models, exactly the same kinds of things you might use in an air pollution study, to run this calculation backwards. But that's the rough approach. Now, the problem, of course, is that firstly, if our model is wrong, if our wind's from the wrong direction, we're going to attribute that source incorrectly. And the other problem is that this is all fine if we only have a couple of potential sources, but if every point is a potential source, then those two red squares are effectively going to be overwhelmed by the range of possibilities. So our ability to constrain the detail, what's actually happening, is going to be very poor. So unless we have a really good in situ network of measurements, and in Australia we don't, we essentially have two, and they're at the edges of the continent, we're not going to be able to do this. And so that's why a bunch of us thought that satellites might be useful. Next slide. So how do the satellite measurements work? Effectively, imagine we're going to use the sun to do this. There's a range of ways this happens, but this is the dominant method that we use for greenhouse gases. We have the sun, and it essentially shines through the atmosphere at a range of different frequencies. And we can use the attenuation of different frequencies to measure the concentration of gases because they have strong differential absorption. The gases will absorb different frequencies differently. And so if we understand the way that absorption works and can kind of calculate out the effects of a whole range of other atmospheric processes, and thereby there's a whole range of careers tied up in that one sentence, we can calculate the amount of greenhouse gas in the atmosphere. And it's a different kind of measurement from the in situ measurement we make at the surface, because it tends to kind of roughly count the number of molecules of the gas along the satellite beam. So instead of measuring nice and close to the surface, it tends to measure this integrated quantity. That has advantages and disadvantages. Let's say in general, the disadvantages are stronger than the advantages. But nonetheless, it has the clear ability to measure wherever there's sunlight and the atmospheric conditions allow. And pretty clearly, obviously the satellite's orbit is going to mean that you've got a decent coverage of the Earth. Let's have a look at the next slide and kind of summarize those advantages and disadvantages. The big advantage is coverage. That, as I said, with the in situ measurements, if you're a long way from a measurement site, you've got very little chance of seeing what's going on. So we've got much less risk of missing unexpected sources. And that's particularly important for greenhouse gases that are capable of surprising us, things like very large emissions of methane. Because you can, in some sense, map a grid of concentrations, you've got a much better ability to localize where a source might be. Because if the wind is coming from a particular direction, then if you're measuring across a grid, you can say, the concentration increases here. So the model is going to localize that source pretty well. The disadvantage is the one I've already mentioned. The strongest one is that we're measuring along the column. So that has a much weaker link to surface sources and sinks than the in situ measurements we could make at the surface. The perfect case would be to measure everywhere just at the surface, but our satellites are not capable of doing that. We'll play games to try and get as close to that situation as we can, but it's not very close. And the other problem is that the satellite measurements themselves are a significant effort. Actually, satellites don't measure these greenhouse gases, they measure radiances that arrive at the satellite, and there's an awful lot of physics involved in getting from that to a measurement of what's actually in the atmosphere, and those are necessarily prone to uncertainties. Next slide. A quick comment on resolution. I've mentioned already that this involves a model to do the back calculation. And so there are effectively two resolutions in play when you're thinking about estimating sources and sinks. How fine a detail can you get? One of them is the resolution of the satellite. So if two sources of two things are happening within the same satellite pixel, then you've got very little chance of distinguishing them. Similarly, you've got a resolution of your atmospheric model, in fact, an atmospheric air pollution model, effectively, an atmospheric transport model. You have little chance of distinguishing two sources that are in the same grid square in that model, and even relatively little chance of distinguishing two sources that might be in adjacent grid squares if the resolution is pretty fine. So you have quite a bit of work to do to trade off or to balance the resolution that's available in your satellite. And you might think, well, let's just go for the finest resolution that we can. You can't do that. There are various technical trade-offs involved in doing that. And similarly, the computational cost of going to the finest model resolution that you can, it's not worth trying to solve the atmospheric problem at resolutions which are much finer than the satellite. Next slide. So roughly, what do we do? How do we actually use these? And at this point, I start to talk about things like Bayesian statistics, and people flee in terror. So I won't do that. But it's a pretty straightforward technique. We basically start with an idea of what we think the sources and sinks might be. So if you like, some sort of inventory, like the inventories that the Australian government might report to international organizations, we run that through an atmospheric air pollution model of some form that calculates a distribution of concentrations of the gases in the atmosphere. We sample the atmosphere in exactly the same way, or as closely as we can, as the satellite does. And that turns out to be quite hard. It turns out we have to mimic the physics that's used to extract the satellite measurements from the atmosphere. But we do that. That's called an observation operator. And then we effectively adjust the emissions, the inventory, to produce the closest match in concentrations that we can. Now, there's quite a few wrinkles in there about how do we know how much to adjust and where and so on, and that's driven by the underlying statistics of the problem. But this is now a pretty well-known kind of technique. It's used throughout these statistics are used in weather forecasting, they're used in seismicity and a whole range of related areas, and they've been applied to this greenhouse gas area for about the last 30 years. Next slide. A couple of examples, and there are hundreds of these internationally. I just picked a couple of Australian examples, and because we're a fairly small community, I was unsurprisingly involved in both of them. Both of them were for students who are working with me. This is from the PhD thesis of Joana Villalobos-Cortez, and she was using measurements from the OCO2 satellite to estimate sources and sinks over Australia. And we basically found that, in fact, the Australian landscape is apparently taking up a pretty significant amount of carbon dioxide. And that's happening in a very diffuse way. If we went out and took an in situ measurement, we probably wouldn't see this. It's because it's spread broadly over the kind of sparsely vegetated and savanna ecosystems of Australia. We're not the first person to have seen this. Various models have been showing this for a while. It's extremely variable. I'm not showing the variability here, but this has turned out that this was a 5-year average. It was driven by one really good year. In a bad year, a lot of that carbon will be lost again. But nonetheless, we think with the satellites that we've currently got, we can see what's happening there. Next slide. Instead of carbon dioxide this time, we're going to look at carbon monoxide. Carbon monoxide is what you get when you burn something incompletely, and it's a major emission product from fires. So we applied measurements from the Tropomi satellite, which measures carbon monoxide, to estimate the emissions from the Black Summer fires. Again, we weren't the only people doing this, and you got what you kind of might have expected. You got very large emissions in southeastern Australia over that Black Summer period. So that was December 2019 and then into January, February 2020. Those emissions, when we actually calculated them out, were significantly larger than what the ground-based estimates were calculating. We think because the ground-based estimates found it hard to actually cover everything. But on the other hand, they were lower than some of the other satellite estimates. And we think that's because in general, they were using coarser resolution and probably couldn't capture some of the detail. But that's an open debate. But these satellites were able to produce kind of more comprehensive attempts at these emissions than doing this stuff from the ground. Next slide. What's the current state of play on observing greenhouse gases? It's a rapidly burgeoning field. Every time I go back and try and do an inventory of how many satellites are actually flying, I find out that there's another one. There's basically probably 8 or 9 satellites currently dedicated to measuring carbon dioxide in the atmosphere. Most of them, or a lot of them will measure something else at the same time, just by measuring it across enough frequencies. And they've been there since about 2009. There's been periods where that's increased rapidly, and there's a pretty solid pipeline of satellites coming down the runway, if you like, that are under production now or slated to fly in the immediate future. Methane is even more. It turns out that methane is a slightly easier measurement to make. Its signal noise from satellites is actually better than carbon dioxide, and so there's now several constellations of methane satellites that are flying and producing quite high resolution coverage, either globally, like the Tropomi instrument, which it's the same instrument we're using for the carbon monoxide, or targeting particular regions. There's a whole stack more essentially coming. The other thing to note is that we often don't just measure these two gases, carbon dioxide and methane, the two major greenhouse gases. We often measure species that are emitted with them, things like carbon monoxide, which is often a measure of combustion, nitrogen dioxide, a pollutant that you get when you burn things, basically. And that's so that we can try and attribute some of the processes that might be responsible for these greenhouse gases. Next slide. What's going to change in the next little while? Largely, it's going to be increased satellite resolution. And that's as we've kind of improved the physics behind the way we do the detection. You can't change a lot of the basic numbers of photons and so on involved, but you can improve the machinery you use to look at them. There's quite a burgeoning area in between the in situ measurements I mentioned at the start and the satellite measurements sitting in space. And that's going to be things like UAVs or drones that can enable us to get some of the advantages of both worlds. You'll never get the coverage you get with a satellite, but you can get a broader spread than you get with just in situ measurements. There's a whole series of new techniques. The methods I've described for doing these back calculations are great, but with the resolutions of satellites now coming down to meters, it can be difficult to apply those methods. It can be difficult to know enough about the atmospheric variation at those resolutions. And so there's a new area of machine learning and kind of automated detection of plumes that we think might be able to work at much smaller resolutions, much finer resolutions. And although I haven't talked about it much here, Caroline gave a hint at the start about another strand of work that I'm really interested in, about integrating this stuff with other Earth observation products, because there's a stack of observations of things like the extent of wetlands that tell us about methane emissions, about the productivity of forests that might tell us about sources and sinks of greenhouse gases, about soil moisture that might tell us about where we can expect biological activity to be happening. And integrating those with these kinds of atmospheric measurements is a really powerful technique. And there's now a series of projects happening across the world that are aiming to try and really apply a very highly integrated view from these things. Next slide. What's Australia's role? It's interesting how similar this is to what Rob was saying. We're mainly a user of other people's data. We're probably going to stay that way. It's interesting to note that there are smaller countries than us that are major players in the space area, like the Netherlands, but they're doing that through very strong partnerships, and the Netherlands being part of the European Space Agency. So the TROPOME instrument that I use a lot was essentially a Dutch designed and built instrument, but they probably would never have done that on their own. So if we're going to play significantly in the satellite area, it's probably going to be in partnership. Calval, however, is where we're really critical. We're the major calibration validation partner for greenhouse gases in the Southern Hemisphere, and we'll probably stay that way. And it's extraordinary just how important that is.
1 minute, Peter.
Good, I'm about a minute from finished. So if we get this wrong about spurious trends in space and time, we're going to interpret those as sources. So it's absolutely critical that these satellite measurements are nailed to highly calibrated ground-based networks. And that's an area where Australia is particularly strong. Next slide. A bit of a plug. So I'm now involved in having sort of proposed some of this stuff back 20 years ago. It's kind of interesting to come back to an application of this. So I'm now involved with a small not-for-profit that's trying to actually generate regular updates to methane emissions over Australia using the TROPOME instrument. And that would never have been possible. We would never have had enough data without the emergence of this remote sensing technology. So there's a link there. It's still in its early days, but if you're curious, you can follow updates as we move towards the launch of that product later this year.
All right, thank you very much. And on to our final talk, where we are coming back down to earth. And we have Dr. Rakesh Devadis. He's a geospatial scientist working with the Australian Bureau of Agriculture and Resource Economics and Sciences, the research arm of the Australian Department of Agriculture and Fisheries and Forestry. Currently, Rakesh leads the construction of a national scale land use data with nearly 18 years of professional experience in the application of remote sensing data for agricultural and environmental monitoring. He's been involved in the implementation of operational projects for state and federal governments, as well as research with universities. Thank you, Rakesh. And I'll let you know when we can see your slides.
Thanks, Carol. I'm trying to share my screen. 1 second.
Okay, you just need to make it slideshow. Whoops, no, can just, yep, looking better.
Is that clear?
At the moment, we don't have the right screen, I think.
Is that the right screen or?
It's the notes screen. Yep, that's good. We're good.
Okay. Thank you. Thanks, Caroline, and thanks for the opportunity to talk here. This presentation, I will focus on our national approach to build land use information for Australia, highlighting the importance of satellite information. Land use is the purpose to which the land cover is committed. And we know the land use activities can result in emissions or removal of greenhouse gases. And land use and land use change these are significant factors mitigating climate change. So building spatially accurate and long-term land use information is critical for resource management and also for climate modeling. We know that satellite-based information is the most widely used tool for land monitoring. And these are some visualization from USGS. We can see that those are the Landsat images taken during 1975 and 2019. And you can see how the Landsat precise and consistent satellite observation can be used for monitoring long-term changes in landscapes. Coming to the land use, land cover, we can look at the patterns using remote sensing and understand the land cover. But deriving land use information, we need satellite measurements and also multiple lines of evidence. On this case, we can see the Google image on the left side, and we can see the catchment scale land use map developed by ABIS. So we can see these are the industrial area and the urban residential area. So in addition to the land cover information, we need multiple lines of evidence to derive these classes. And we know the implication of these sort of land classes on climate. And another example is, again, it's from an agricultural area. Google image on the left side, catchment scale land use on the right side. You can see these are the grazing, native grazing areas. These are the irrigated agriculture. This is dryland agriculture, and this is production area forest. Again, we need multiple lines of evidence to get to this sort of information, and that's what the land use data can provide. So, Australian Collaborative Land Use and Management Program coordinates the national efforts on land use mapping and land use, land cover, and land management practices since 1999. And the National Committee on Land Use and Management Information, NCLUMI, coordinates these activities, and ABIS leads this program. And there are a number of partners from our state and territory agencies contribute to this data, including UNE's Agriculture Division. So these are the two land use products published from ABIS. On the left side, you can see the catchment scale land use data, which is collaborative efforts, like state and territory agencies provide data, and we collate that data at national scale to produce the catchment scale land use data. Because the data are provided from different agencies, there are some difference in the methodologies of construction. And so it is ideally used for a regional application. But on the right side, this is the national scale land use data, which uses a nationally consistent method, particularly on the input data and statistical models to create that data. So this is published typically in every 5 years. The core input data into this is the TerraMODIS satellite information. And so that data is published currently at 250 meters data. This is more of useful in the strategic planning and continental applications. So the classification system is called Australian Land Use and Management Classification. This is a three-tier system, which 6 primary classes, and the intensity of classes increases from 1 to 5, and there's a water-related class. So the 6 primary classes are split into 38 secondary and 197 tertiary classes. So there is a long history of this data production. We have about 10 published data sets already. We are working on the current version of 2020-21, and these recent versions contribute to the national land accounts carried out by ABS and DQ. So the construction of the national scale land use data is achieved in 2 steps. The first step is to get the non-agricultural land use. So for that purpose, we create 7 thematic layers. One is the protected areas, topographic features, catchment scale land use data, which I mentioned earlier. Land tenure data is another data set produced by ABS. Then urban boundaries from mesh blocks, ABS mesh blocks, and then forest type data, which is generated from state forest report published by ABS, and then stock routes. So these 7 thematic layers are stacked, and we do a spatial overlay analysis. So we get a unique combination of these pixels, and we apply an expert rule based on our previous knowledge to allocate non-agricultural land use. Coming to the agricultural land use, this is more of a modeling approach. So we have 3 core data sets. One is MODIS measuring, ground reference data, and then ABS agriculture census. So sorry for that animation. It's moved from Windows to Mac. So the core, the main data sets is, as I mentioned earlier, it's MODIS imagery, which we use a Mode 13 Q1 product. NDVI data 250-meter resolution, and then we have the ground reference data collected from a number of state agencies. So these 2 data, and then ABS agriculture census, which we use to constrain our spatial allocation of different agricultural land use. So these 2 data sets, we can derive temporal signatures. So these temporal signatures are the core thing, like, that's the main factor help us to identify different land use. And we use a Bayesian and both a machine learning approach. So we can see, I can show you, because temporal signatures is the main component of this modeling approach. I can just show a snapshot from some of the prominent crops or land use we use. So we can see the seasonal and the summer winter seasonal differences and the peak timing of different crop growths. So all this information feed into the models we use to allocate agricultural land use.
1 minute, Rakesh.
Almost done. So another direction we are looking at is using artificial intelligence and machine learning applications. And again, there's a huge demand for high resolution satellite data. So this is a project we are carrying out recently because of the benefiting the Digital Earth Australia and NCA platforms to using Sentinel-2 satellite time series satellite information to map almond crops. And this is another example of how long-term land use data can be used for understanding the long-term changes in the land use. So here we can see from 1989 to recent, where we can use a combination of Landsat and land use information can be used to look at how forest land is changing, grassland is changing, and settlements are changing. So we know that there's a long-term implications of these sort of land use changes on our climate models. With that, I will conclude here. So from the methodological point, we are definitely looking at going for a finer resolution data. We are trying to bring more of AML techniques, and we are also seeking wider partnership, including private partners like the data farming and DAS. And also, this is one core thing, like, and we all know that ground reference information is the most important thing determining the accuracy of the model. So we are also trying to collaborate more for collecting and sharing ground reference information. So I'll conclude with some of the new project initiatives we are having now, like ABS is developing a spatial economic land use modeling capability to analyze the impact of domestic and international climate-related policies on agriculture and land use at a regional scale. And this is from our state partnership, Victoria, developing agriculture climate spatial tool, which will integrate land use information into biophysical models to support management of climate variability. Thank you. So these are some of the visuals from our recently published land use data, and we can look at that because if there's long-term data availability, we can look at the changes happening in our landscape. Thank you.
Thank you very much. Okay, and just while we're here, let's give a big hand clap for all our speakers today. A really diverse, interesting number of talks. So we went a bit of overtime, but fortunately, people have been answering the questions in the chat, and I think there's only one question left. It's for Peter. The question is, I was intrigued from your students 2015 to 2019 average, well now it's, I just lost the question. Okay. Average CO2 flux map as to why the Australian eastern coastal area around Sydney is a strong net source of carbon dioxide, but all of Victoria, even Melbourne, is a relatively strong net CO2 sink. Any thoughts on why this might be?
So the Melbourne thing I can answer fairly easily, and that's just a question of resolution. We don't have enough resolution to really pick up the city clearly in the OCO2 observations. It's actually quite hard work to see cities. So what that's actually telling us is that, yeah, there's a sink. It's probably due to the forests sitting around southern and central Victoria. Now, why Sydney turns out to be a source, we don't know. And we've actually looked a little bit at the time structure for that source, and it's pretty episodic. There is always a possibility of instrumental problems that might be involved. It's one of the things we'd have to stare at pretty hard. But at the moment, I'd have to say we're not really clear on what's happening in the Sydney case. The Melbourne case, I think, is probably a case of it's doing what forests do over Australia, and we don't have enough resolution to really see the cities. Now, it's also worth pointing out that this calculation stopped just as the Black Summer fires were starting to kick off. I think the size of the carbon fluxes that we saw in those fires would have changed that picture quite a bit.
Thank you so much, Peter, and it's lovely to see you after all these decades.
That was Helen. We've got one more question, I think, which we can fit in before we end. And I don't know if someone wants to volunteer to take this. Maybe Anthony, could we not have an Australian EOS equivalent of NASA Earth Observatory so the general population can learn what is happening across Australia and the surrounding oceans?
Thanks, Caroline. It's a good question. I mean, I think we have something like that in an aggregated way, right? I mean, there are data portals available for ocean data. You know, you can access a lot of climate data from the Bureau of Meteorology, from the Australian Climate Service. So I think, yeah, I mean, what might be missing is a one-stop shop, but let me be the last person to suggest that we need another data portal in Australia, the last person. Thanks.
All right. Okay, but yeah, I'd love the idea. We've got one final question here for Rakesh. Has there been any use of high-resolution satellite imagery for agricultural maps of biomass estimation of individual farms? If so, which satellites could be used for plant-level information?
Caroline, I don't think we use, we are developing techniques to measure biomass at the national scale. So currently we are focusing on getting our crop mapping correct so that we can go to the next level. Thank you.
Okay, so potentially a gap there. Okay, so it's 1:30, so I'm going to wrap up, but you might be able to get your questions in the chat and answered in the next 5 minutes if the speakers can hang around. So thank you all for attending. I thought it was really interesting talks. I could see that Earth observations, they're just not delivering trends, but really regional point-based information on how our environment is changing. A number of speakers mentioned how important Australia was for calibration and validation, and there was a lot of combining of different satellite observations for all the different products. And I think I heard ML, as always, mentioned a couple of times. So I think we took quite a narrow definition of climate variables for this seminar, but of course there are many other sort of climate related applications, drought monitoring, marine heat waves, monitoring greening of cities. So they're all part of the bigger climate picture. And I think we'd all be quite keen to have a community that is a lot more collaborative and transdisciplinary. And I think there are some good examples of that today. So thank you very much again.